Hello everyone. In the previous session we have proved one of the theorem that there exists a non-measurable set in closed interval 0 and open interval 1. So you just go through that theorem that what we have proved there exists a non-measurable set in closed interval 0 and open interval 1. Now where I have used a logic of equivalence relation in order to prove that theorem. This theorem is also one of the application of the same, but somewhat is modified. Rest of the proof will be same. So let me continue with that. Here is a statement of the theorem. Every set of positive measure has a non-measurable set. So meaning is that if I have any set E which is having a positive measure, then there will be a non-measurable set inside this open set E. Suppose if I have an open set E which is having a positive measure, then we have to prove that there is one more non-measurable set inside this E. That is what given R. E is any set of positive measure, then we have to prove E as non-measurable set. Now let me prove the theorem. So first let me write the given that E is positive measure. So I'll write all the steps in, I'll give all the steps in notes, but I'm not going to write all the steps here. Then if E is positive measure, then let me take a closed interval AB. Then there exists any set E1 such that E intersection AB. In the sense, this set E1, if I'm going to choose a closed interval AB, this set E1 consists of a common element between the assumed set E and a closed interval AB. So I have defined a set E1 as E intersection closed interval AB. Since E is measurable, so I can say E1 is a positive measurable set, or E1 is measurable. Fine. Now let me define equivalence relation. So I have already done this in a previous theorem. You just go through that. So let me define equivalence relation on E1 in such a way that X is related to Y in E1. X is related to Y in E1. If same relation I'm going to define, where I have defined that the difference is a rational number, right? Here also I'm going to write the same. Meaning is two numbers will be related to one another in set E1 only when their difference X minus Y is a rational number. Fine. So in the previous theorem I have already proved that this is a equivalence relation. So here no need to prove that again. I have already proved that the symbol is equivalence relation for a given relation. Fine. So this is already done, that it is reflexive, symmetric and transitive. So again no need to prove, since their difference is rational number, it is always an equivalence relation. If that was the case, as I already explained, a set E1 can be expressed as union of all the equivalence classes. Equivalence relation, and have chosen that set as P, right? You just go to the previous theorem, then you will understand very well where I am using the same concept. So I am doing the same for this also. So let me consider P as a set of all equivalence classes where all the elements inside this will be satisfying equivalence relation. So I can write E1 as this. Fine. Let me take where I have chosen Ri, right? Here also I am going to choose the same. Let Ri R is equal to 1 to infinity be enumerable set of rational numbers. Same concept. So I have considered a set Ri as a set of rational numbers and the interval -1 and +1. Why? Because here I have chosen a closed interval AB. So let me take it as -1 and +1. Now I am going to define a translation modulo as it is a non-measurable set. I have explained this in a previous theorem. If you understand that very well, you will understand this theorem also. So I can define Pi as P translation modulo R, where R is a rational number. Why? Because Ri I have taken as enumeration form of a rational number. So R in the element R is also belonging to the same set Ri. Then I can clearly write that Pi can be expressed as subset of A minus 1 B plus 1. This is I have told you at the beginning itself. So since I have taken a closed interval, one element outside and one element right to this element I have to take. So that is what I have chosen here. Fine. Now I can write Pi as union of all the i's. Pi is also a subset of A minus 1 and B plus 1. Moreover, all the Pi's are disjoint. So same concept I am using here. Pi's are disjoint. So I can write Pn intersection Pm is equal to null set. And let me take one element. In the meaning of disjoint is their intersection is null set. Let me take any one element in their intersection. That is, if X belongs to Xn intersection Pm, Pn intersection Pm. If this element belongs to intersection of these two, then definitely X will be in the first set. Also X will be in the second set. Fine. Now how I have defined pi as p translation modulo r. Similarly, now I can write x belongs to pn is none other than p translation modulo rn. I'll write this as p translation modulo rn. Since x can be expressed as p translation modulo rn, why? Because x belongs to pn. I have defined pi as p translation modulo r. Clear? And now y belongs to, suppose if y element y belongs to p, I can replace this with y. So I can write x as y translation modulo rn. Similarly, let me take an element z belongs to p. I have proved all these things in the previous theorem. If you understand, I am telling you again and again. If that theorem was clear, you can understand this very well. So now let me take x is equal to z plus rm. Z translation modulo rm. Why? Because I have chosen y for this case, and for pm case I have chosen z for z in the set p. So I can write like this: x is equal to y translation modulo rn and x is equal to z translation modulo rn. Now by combining these two, since LHS is equal, I can write that y plus r, y translation modulo rn is equal to z translation modulo rm. Fine. Again, if you're going to take difference of this, since Rn and Rm are also rational number, addition of rational numbers is also rational number. So I can say that y minus z is also a rational number. Fine. Y minus z is also rational number. Now, so I can write y is equivalent to what we say, y is related to z. So or else I can say y is equivalence relation on z. Now let me consider ei, which is subset of union of all pi. Clear? What I have assumed is I have taken an element ei as subset of pi. So E is any arbitrary element. E is any open set. Now let me take any arbitrary element x in that particular ei. Fine. So we have already proved that since I have proved y is equivalent to z, similarly we can also prove that x is equivalent to y. So by these two conditions, I can directly write x is equivalent to y, which is equivalent to z for any element z belongs to p. Clear? Now suppose if x is congruent to z, I can write that as per the defined relation x minus y should be equal to rational number, right? That is how the relation is defined. Fine. At the beginning itself I have told you x is related to y only when the difference is a rational number. So when x is related to z, I can say x minus z is a rational number. Let me say that Ri. So by modifying this, I can write that as x is equal to z plus Ri. I have shifted this element. If z belongs to p, I can write z plus. If z belongs to p, I can write z plus Ri also belongs to p. I'm repeating once again. Since x is related to z, as per the defined relation, I can write x minus z is rational number. Fine, I have shifted this element. Since z is in p, if you're going to add any rational number to z, again that element will be in p. Since I have added a rational number Ri to z, so I have obtained the element which is again in p. Meaning is that since x is an element in E, fine, and x is belonging to the set p, so I can say that x belongs to union of all pi's. Again x is in a set E. Further from that I can write E is subset of union I pi. Clear? Suppose that if P is measurable, whatever the concept I have used in previous case, I am doing the same. As per the previous theorem, I can write, you just go to the proof of the theorem. I have done this statement, M of Pi is equal to M of P. I have done there. Now, if P is measurable, what will be the case? Let me see. Then, measure of E1 will be less than or equal to measure of union I Pi. Fine. Again, which will be equal to summation measure of p. Why? Because union of all the pi's I have taken as p. Moreover, measure of pi will be equal to measure of p. So that is why I have taken union as measure of p. In the previous theorem, I have proved that this value will be 0 when measure of p is equal to 0. You just go to the theorem. I have proved there clearly. This value, measure of this p will be 0. I can write here I summation MP will be 0 when measure of P is equal to 0. In the sense, measure of PI is 0 when measure of P is 0. And it will take infinity if measure of P is not equal to 0. In the sense, for all greater values of 0, it will be infinity. And I have clearly proved this in the previous theorem. Fine. So in this case what I have assumed is P is measurable, right? Suppose if P is measurable, what will be the case? I can express union of all the Pi's as subset of A minus 1 and B plus 1, right? I have assumed this here. See here, if P is measurable, this condition holds good. Then I can write measure of union I, Pi can be written as, which is less than or equal to, measure is none other than, let me write one more step, A minus 1, comma B plus 1. Measure is none other than difference. So let me take the difference. Measure is none other than length. So I'll let me find the length, then you will get something like this. So it will give us minus A plus 1. So B minus A plus 2. Clearly this is a definite quantity. In the sense measure is less than. I mean, what can I say? We have obtained a measure of this interval. Fine. So, but which is a contradiction. Why? Because we have assumed that P is measurable. Fine. But what we have arrived is that measure is less than or equal to B minus A plus 2. Why? Because either measure of Pi should be equal to 0 or it should be equal to infinity. But what I have arrived is that if P is measurable, I have obtained the length as B minus A plus 2, which is not the case that we have chosen. So it is contradiction to our assumption that P is measurable. Therefore, the only possibility is P is non-measurable. P is non-measurable. So what I have chosen is P is non-measurable. We have to prove every set, E is a set which contains a P as a subset. Right? Somewhere here I have assumed. See here, E is subset of P. So if P is non-measurable, I can say E has at least one set which is non-measure. That is what we have to prove. E be any set which is of positive measure, then E should have at least one non-measurable set. What I have chosen is E is subset of Pi. I have proved that P is non-measurable. If P is non-measurable, since E is subset of Pi, so E is measurable, but it has at least one non-measurable set. Non-measurable set. So that is what I have proved. Now the next concept is measurable function. Measurable function. So you have come across outer measure and measurable set or Lebesgue measure set. Now it is measurable function. So it is important. It is asked in one of the year. I don't remember the year exactly, but it is important. So an extended real valued function f from e to r union minus infinity to plus infinity, extended function f from a set e to r union minus infinity to plus infinity, when you combine r real number with minus infinity and plus infinity, defined an any measurable set E in R, is said to be measurable. I'm repeating once again. Any function f defined from a set E where E is a measurable set. Fine. Measurable set on R is said to be measurable if for any real number alpha, the set x belongs to E such that f of x is greater than alpha is measurable. I'm repeating once again. If a function is defined in such a way, and if for any real number where E is measurable, and if for any real number alpha, if this set is measurable, in the sense an element x in the set E, measurable set E, and f of x, image of x, is greater than alpha is measurable, then we say a given function f is measurable. An extended real valued function f is measurable only when this set is measurable. I'll give you a simple example. A constant function f from e to r star. Suppose if I define a function f from e to r star will be where e is measurable, then f is also measurable. Example is a constant function f defined from e to real number r is measurable. Where E is measurable, then f is also measurable. Clear? In the next session, you just remember this definition. In the next session, let me solve the theorems based on measurable function. Thank you. Continue in the next section.